Physics is physics across scales, and we all use the same mathematical language, and we all have the same great laws somehow. And this is why there's so much added value when you put people together from different fields and from different angles, so to speak.
When we make progress, it's quite often by making connections between different branches of physics, or exchanging ideas, or finding that certain methods that were developed in one area can be applied somewhere else. And this is precisely also now what's happening today.
We should not be thinking anymore in terms of our own physical range of parameters, like I'm doing physics between micrometer and nanometer length scale. That doesn't make sense anymore.
We really believe in the unity of physics.
Now is the time to try to join forces again. Have one institute for theoretical physics, the Delta Institute.
With Amsterdam, Leiden and Utrecht. We really are of a size and we have the expertise in overlapping areas of theoretical physics that we can really complement each other in a tremendous way.
And so there's this cross-fertilization, this exchange of ideas. And that takes place at all levels, smaller levels, larger levels, and that's what we try to really promote within the Delta Institute.
The thing about these collaborations is that, when you're working on a problem and you get stuck, you sort of walk out, you go down the corridor and you try to find somebody who can help you with your problem, and you have a discussion. And now the corridor just got a lot longer.
There will be new things emerging out of this symbiosis that we are creating with these three institutes.
We don't know yet exactly how it is going to emerge, but this is what we hope, some collective phenomena that is more than just the sum of the three institutes here.
By being together, 1 + 1 + 1 is going to be much more than 3.
And who knows, we have in the real ambitious plan of things, we say that by really joining forces, we might come up with amazing discoveries.
Yes, it's better than ever in physics since I started my career a long time ago. Yeah, it's a really exciting time right now.
I think at the moment it's a nice time to do physics and theoretical. There are many interesting things going on.
High-TC superconductivity is a very, very important project, I think, to figure out how that works.
If we really want to apply superconductivity, you want to have that at room temperature, and then we can use that.
We have been trying during the last years to construct a quantum computer.
You could imagine having this massively parallel calculation where you don't have just one computer, not 1,000 computers, but billions of computers, all in one chip, all carrying out this calculation in parallel and delivering the answer in record speed. So that's the dream. That's what's called quantum computing. It's a very exciting field of research.
The Big Bang is we don't know what the Big Bang is.
The Big Bang is a place where ordinary gravity breaks down because the temperatures are very high and so on. So in order to understand the Big Bang, we need a theory of quantum gravity.
A theory that unites gravity with matter, with quantum mechanics.
There's a mathematical description for the one, there's a mathematical description for the other. Okay, put them together. But if you do that, you get utter and complete nonsense.
I mean, if you look at cosmology, where we have these very big questions regarding dark energy and dark matter, where we don't understand 96% of all of the energy in the universe, that to me is already a hint that we are overlooking a lot in the structure of space-time, and particularly regarding gravity, of course.
Gravity, as we think we understand it, is necessarily incomplete.
So we know that out of all the matter in the universe, about 85% is in the form of dark matter, which is fundamentally different from anything we have ever discovered so far.
There's a very fundamental question: what does this dark matter consist of? What is it made of?
That's so interesting about dark matter. Huh? We'll figure this out in the next 10 years.
Finding dark matter would really solve one of the big mysteries of modern science.
To be a successful researcher in theoretical physics, you really need a very broad combination of talents. You need to be extremely at ease with mathematical formalism. You need to have also very good physical intuition that allows you to apply the knowledge that you have to the solution of real-world problems, and also to come up with new problems.
Without young people, the field is dead. There's no physics anymore at some point.
I think it's even more important for me than for them. They don't even realize how much they are bringing with their life and with their questions, with their energy and their wish to learn.
It is very important that new ideas come in, new people come in, that are willing to kick your ass, to tell you that you're an old idiot who is stuck in his ideas. That's extremely important to keep the field active, fresh, and to really make progress. So it's essential.
So the idea behind the talent plan of the DITP is to bring to the institutes here the upcoming generation of researchers, of people who have such talents.
It's the best place one can be. I mean, having all these researchers together and being part of this highly selected team, it's the best one can wish and the best one can get, I think.
We were not going to train professors. Right? I mean, we train problem solvers. And so someone with a degree from our consortium has learned problem solving, has learned the unity of a broad range of science, knows where to find answers if they're just a little bit outside of his own expertise. And this is a skill which we know already is immensely attractive.
These days, research is very often stated in terms of its deliverables. Yes, what are we going to make? What the Delta ITP runs over 10 years. What will we have at the end of this period? I don't know.
So we are doing fundamental science. And I think although one cannot see immediately what is it good for, what we are investigating right now, this answer will come in 50 years. But if we don't do it now, research will stop and we will be stuck at a certain point.
We're going to produce good science, high quality science, and creating a competitive scientific institute that is of top quality in the world.
And who knows, we may give back one Nobel Prize. But that's not something we can really plan. And so the people is something we can plan and promise, and a Nobel Prize, that's our dream.
I think we are in a very exciting period. I mean, if I look back in physics, you might say, I mentioned quantum mechanics, I mentioned general relativity, or the development of the Standard Model. When I started out, I thought, well, it would have been enormously exciting to live in a period when these kind of things are happening. I have a feeling we are now at the beginning of a development of that sort.
Physics right now, or this part of physics, is perhaps entering this breakthrough era. There's a lot of good work to do right now, and so it feels good. It's a place where you would like to be, I think.
I feel like we are like adventurers, basically. At the frontier, instead of being at the frontier of some, remote land, we are at the frontier of knowledge, basically. And I really like this feeling of, being able perhaps to contribute to knowledge and to push a little bit that frontier.
We can always find new questions, and what we learn always gives new horizons, and those things keep growing. And this is also why I don't really believe that we will find this moment when we say we have answered all questions. We have the theory of everything and now it's done. So physics to me is not a thing that will end.